Today let us see the effect of temperature stresses in composite bars. Most of the material expands when the temperature increases and contracts when the temperature falls. Almost all metals expands by the increase in temperature. And the change in length of the member is directly proportional to the change in temperature as well as the original length of the member. That is delta. Delta is proportional to change in temperature T and length of the member. And the coefficient of proportionality or the constant of proportionality, it is alpha and it is called coefficient of thermal expansion. And we can define the coefficient of thermal expansion as change in unit length of the material due to unit change in temperature. This table shows the coefficient of thermal expansion of different metals: steel, copper, stainless steel, brass and aluminium. Then if the free expansion is per meter, then there will be no resistance against the changes and hence no stresses will be developed. You know, the stresses will be developed when a resistance against the deformation. Then that free expansion will be alpha T into L. Alpha is the coefficient of thermal expansion, T is the change in temperature, and L is original length of the member. But if the free expansion is prevented fully or partially, then stresses will be induced inside the bar, and these stresses are known as the temperature stresses. Now let us consider the case of a bar restrained at two supports as given in this figure. And if it is not restrained here, there would have been a free expansion given by alpha T into L. Since the support prevents this deforming free expansion, then in order to prevent this increasing length of the member, there should be certain compressive forces developed, and the magnitude of that force, it is represented here as P. And the magnitude of P should be such as the decrease in length due to that P should be equal to alpha TL, or delta, that is PL by AE, that is equal to alpha TL. And from this we can obtain the expression for the temperature stress. As you know, the stress is given by force by area, and from this P by A, which is represented as stress small letter P, that is equal to E alpha T. This will give the expression for the temperature stress due to a change in temperature T, and E is the modulus of elasticity of material, and alpha is the coefficient of thermal expansion. Now let us consider the case of a bar which is prevented partially. Here we can consider a bar of length L, and it is L, the free expansion by an amount delta is per meter. Then it is restrained. Restraints are provided here. If there are no restraints due to change in temperature T, the free expansion would have been alpha TL. But only up to delta is per meter here. So the expansion prevented is alpha TL minus delta. That is the expansion prevented. And due to this prevention, the stresses will be induced inside the bar, and the stress is caused by the force P, the compressive in nature, because the length has to be decreased, and the magnitude of force should be such that it should provide a deformation such as equal to alpha TL minus delta. So we can write PL by A is equal to delta, which is alpha TL minus delta. From this we can obtain the expression for the temperature stress, which is given by P by A. That is E by L into alpha TL minus delta. That will give the magnitude of the temperature stress when the free expansion is prevented partially. Now let us consider the case of thermal stresses in compound bar. In the case of compound bar, there will be more than one material and they will be firmly connected. And when the temperature rises, the two materials of the compound bar, then free expansion of both will be different. Here we have the bar 1 and bar 2, and it is, let alpha 1 be the coefficient of thermal expansion of bar 1 and alpha 2 the coefficient of thermal expansion of bar 2. You have already seen that for different materials the coefficients of thermal expansions are different. So the free expansion of these two bars will be different. But they are prevented from separating and the two bars should have final common position. This is possible only by the extension of the bar which has less free expansion and contraction of the bar which has more free expansion. Here we can consider that alpha 1 is equal to is greater than alpha 2. That is, the free expansion of bar 1 is more than free expansion of bar 2 because the free expansion is given by alpha TL. Free expansion of bar 1 is alpha 1 TL and free expansion of bar 2 is alpha 2 TL. And since alpha 1 is greater than alpha 2, free expansion of bar 1 is more than free expansion of bar 2. Here alpha 1 TL is marked here, which represent the free expansion of bar 1. That AA that represent the final position of the bar 1 if it is allowed freely in and independently. Then free expansion of bar 2, it is by an amount alpha 2 TL. Since alpha 2 is less than alpha 1, the final position, if it is allowed to expand freely, it would have been BB. But both bars should have same final position because they are prevented from separating. Let this CC represent the final position of this compound bar. Then bar 1 has to be compressed to reach the position ZC, whereas bar 2 has to be elongated from BB to reach the position CC. So the type of force in bar 1, that is P1, should be compressive in nature. So the stress developed in bar 1 will be compressive. And here for bar 2, there should be a tensile force of magnitude represented here as P2 and the stress developed in bar 2, that will be tensile, such that the final position of the composite bar is CC. Now let us consider the equilibrium of forces. P1 is a compressive force bar 1, P2 is compressive force in bar 2. For the equilibrium of forces, P1 should be equal to P2 and let this be equal to P. Now let us examine the case of bar 1. CC is the final position and the net expansion of bar 1, that is alpha 1 TL minus delta 1, where delta 1 is decrease in length due to the compressive force P1. So alpha 1 TL minus delta 1 is the distance up to CC while considering bar 1. Now let us consider bar 2. The free expansion is alpha 2 TL and the final position should be ZC, and let delta 2 represent the increase in length due to the tensile force P2. So distance up to CC considering bar 2, it is alpha 2 TL plus delta 2. From this we can take the terms delta 1 and delta 2 to the left side and the remaining terms to the right side. Delta 1 plus delta 2, that is given by alpha 1 TL minus alpha 2 TL, that is alpha 1 minus alpha 2 into TL. Here what is delta 1? Delta 1 is a decrease in length of bar 1 due to the force P, which is given by P1L divided by A1E1, that is delta 1. And delta 2 is an increase in length of bar 2 due to the tensile force P2. So delta 2 is given by P2L divided by A2E2. L for both are same because both bars have the same initial length and final length also should be the same. That's why we are considering CC as the final position. So we can write PL by, then already we have obtained that P1 is equal to P2 and we have represented that as P. So here we can substitute PL divided by A1 E1 plus PL divided by A2 E2, that is equal to alpha 1 minus alpha 2 into T into L. And from this, we can find out the temperature stresses in both materials. Here, alpha 1 is coefficient of thermal expansion of bar 1, alpha 2 coefficient of thermal expansion of bar 2. Then T is the change in temperature, L is the initial length of the bar. In this derivation, we have taken alpha 1 is greater than alpha 2. Now let us do the problem. A bar of brass 20 mm is enclosed in a steel tube of 40 mm external diameter and 20 mm internal diameter. The bar and tubes are initially 1.2 meter long and are rigidly fastened at both ends using 20 mm diameter pins. If the temperature is raised by 60 degree, find the stresses induced in the bar, tube and pin. Modulus of elasticity of steel and brass are given, as well as coefficient of thermal expansion of steel and brass are given. Here we can see that the coefficient of thermal expansion of brass is more than the coefficient of thermal expansion of steel, and hence the free expansion of brass will be more than that of the steel. And here the figure. Then at the center we have a steel tube. At the center we have a brass bar and the diameter is given as 20 mm, and at the outer we have the steel tube of inner diameter 20 mm and outer diameter 40 mm. And look at the figure, and the length of the member is given as 1.2 meter. Since alpha B, that is coefficient of thermal expansion of brass, is more than that of the steel, free expansion of brass is more than the free expansion of steel. That is AA. We have the brass here. Then this is the steel tube outside the brass bar. Okay, AA represent the free expansion of brass, whereas BB represent the free expansion of steel. And here CC represent the final position. Then alpha B into T into L, that represent the free expansion of brass, whereas alpha S into T into L, that represent the free expansion of steel. And both should have the final position CC. From this we can write, before that we can mark the forces here also. Here, in order to have the brass to reach the final position CC, there should be a certain compressive force, let it be equal to P1, and for steel to reach the final position CC, there should be a tensile force P2. Then, as we have seen in the derivation, for the equilibrium of forces, P1 should be equal to P2 and let it be equal to P. And here delta V, because of this force P, the compressive force P, the length of the member brass get reduced, and delta B, that is the decrease in length of brass because of force P1. Here delta S is the increase in length of the steel due to the tensile force P2, and we can write, considering brass, we can write alpha B into T into L minus delta B, that is equal to alpha S into T into L plus delta S. This is because both should have the final position CC. If we consider the brass, then delta B into T into L, that is a free expansion and is up to the position AA. It has to be compressed by an amount delta B to reach the position CC. That's why the expression like this. Now considering steel, the alpha S into T into L, that is the free expansion of steel. It has to be stretched from BB to reach the position CC, and an increase in length due to the force, tensile force P2, that is delta S. That is why alpha S into T into L plus delta S. We can equate these two and we can find out the force P, and from this we can obtain the temperature stresses. Then in order to substitute in these expressions, we can find out the areas, all these things. Then substitute in this expression, delta S plus delta B is equal to alpha B into T into L minus alpha S into T into L, that we obtained here that is equal to alpha B minus alpha S into TL. And delta S that is equal to PL divided by AS ES, that is increase in length of the steel due to the force, tensile force P, and delta B that is given by PL AB into EB, which is a decrease in length of brass due to the compressive force P. Then substitute the values of alpha B, alpha S. Then increase in temperature is given as 60 degree and length of the member is given as 1.2 meter. And we can substitute the value of AS, that is area of steel. It is a steel tube of inner diameter 20 mm and outer diameter 40 mm. And area of brass rod, which is of diameter 20, the area is given by pi by 4 into 20 square. Substitute all these values, we can obtain the value of P, that is this force is compressive in brass and tensile in steel. Now we can find out the stress in steel, that is P divided stress is given by force by area, force divided by area of steel. Here the stress in steel, it is tensile, and stress in bar, that is P divided by area of brass, then which is compressive. Now you are asked to find out the stress in shear stress in pin. Then shear stress is given by force divided by twice the area of pin. There are two areas resisting the shear. Then the pin is of diameter 20 mm and force divided by that area of the pin, that will give the shear stress in pin. Now we can move on to next one. A compound bar is made of steel plate 50 mm wide and 10 mm thick, to which copper plates of 40 mm wide and 5 mm thick are connected rigidly on each side. That is, here in the figure, at center we have the steel and at top and bottom we have the copper plates. And the steel plate, it is of width 50 mm and the thickness of the copper plate, it is given as 10 mm, whereas the steel plate is of thickness 10 mm and the copper plates they are of thickness 5 mm. Now they are connected rigidly on each side as shown in figure. Then the length of the bar at normal temperature, it is given as 1 meter and the temperature is raised by 80 degree. Determine stress in each metal and change in length. Coefficient of thermal expansion of steel, it is given as 12 into 10 raised to minus 6 per degree centigrade, and of copper it is 17 into 10 raised to minus 6 per degree centigrade. And modulus of elasticity of steel and copper are given. Now looking into the coefficients of thermal expansion, first you have to do this one. You should find out which one will expand more. That depends upon the coefficient of thermal expansion, because the free expansion is given by alpha T into L. The change in length is change in temperature is the same. Length of the both metals, they are same. So it purely depends upon the coefficient of thermal expansion. Here the coefficient of thermal expansion is copper is more than that of the steel. So copper will expand more. That is at the top and bottom plates that will expand more, and its final position is marked as AA. And coefficient of steel is less, so it will expand less, and its final position is marked here as BB. Now in the copper plate, there should be compressive forces developed to reach the final position C, whereas in the steel plate, there should be tensile force to reach the final position C. Now we can consider the equilibrium of forces. Then 2Pc is acting towards left side, that is represented as compressive forces, and it should be equal to the tensile force Ps. So Ps is equal to 2 into Pc. Now let us consider the case of steel, and the final position is Cc. Then alpha S into TL, that is a free expansion of steel, and it has to be increased by an amount delta S to reach the final position CC. So alpha S into TL plus delta S, that should be equal to, the next one we will obtain by considering copper, then free expansion of copper, that is given by alpha C into TL, and it has to be decreased by an amount delta C by this compressive force PC to reach the final position CC, that minus delta C. From this we can write delta S plus delta C is equal to alpha C minus alpha S into TL. And delta S, that is given by PSL by ACS, and delta C, change in length of copper due to the compressive force PC, that is given by PCL by ACAC, that is equal to alpha C minus alpha S into TL. Now we know that force in steel, that is equal to twice the force in copper. We can substitute that. Then from this we can find out the value of force in copper as well as the force in steel. Force in copper, it is compressive, and force in steel, it is tensile. Now the stress in copper is given by force in copper divided by area of copper, and the stress in steel is given by force in steel divided by area of steel. Steel, it is tensile. Stress in copper, it is compressive. Now you are asked to find out the change in length of the compound bar. Change in length is either given by alpha S into T into L plus delta S, or that is again equal to alpha C into T into L minus delta C. Both are same because the final position is CC. You can obtain from this. You can substitute the value of coefficient of thermal expansion of steel, increase in temperature T, length, initial length of the member L, as well as all these values we have obtained PS, that is the tensile force in steel, the length of steel, area of cross section of steel, as well as modulus of elasticity of steel. That will give the change in length of the member. Thank you.